Hello again. Doing dynamics review, and this looks to be about net force and adding vectors. So they tell us there's two forces acting on each of these horizontally, and they say here to just not worry about forces in the vertical direction. So just stuff in the x direction. And they're telling us this object is stationary. If you're stationary, it means you're not moving, and to stay that way, you'd have to not be accelerating. So that would mean that our acceleration is 0. And if we write Newton's second law for this, F net equals ma. The F net is made up of these two forces, F1 and F2. So if we fill that in, sorry, I need to erase because I don't have a lot of room. The F net would be F1, which is negative 10, plus F2, I don't know it, equals the mass. They didn't say what it is, but the acceleration is 0. So we get negative 10 plus F2 equals 0. Take 10 to the other side, or add 10 to each side, and we get F2 must be positive 10. So either positive 10, or you could say 10 to the right. And the net force would be negative 10 plus positive 10, which makes 0. That's how we're going to solve all of these, is just Newton's second law and then fill in the blanks. Now, moving right at a constant velocity and stationary mean the same thing to us as far as acceleration. They both mean your speed isn't changing, therefore your acceleration is 0. So when we go to do Newton's second law, F net equals ma. The net force is F1 plus F2 equals ma. F1 is negative 5, that's 5 left, plus F2 equals, we don't know the mass, but the acceleration is still 0, so all good. And from that we get negative 5 plus F2 equals 0, F2 is 5. So it's positive 5, or we could say it's 5 to the right. Okay. Next one, they say we're accelerating to the left, and this time they give us the net force. So we say F net equals ma. The net force is made up of F1 plus F2 equals ma. F1 we don't know. F2 is 10 to the left, so negative 10 equals. Now, they don't give us the mass or the acceleration, but they tell us that combined they make negative 25. So we don't know mass or acceleration, but they tell us that these two forces have to combine to minus 25. That will be enough. If we want F1 alone, we want to get rid of this negative 10, so we add 10 to each side, and we get F1 equals negative 15, or 15 to the left. All right, so 15 newtons left plus another 10 newtons left adds up to 25 newtons left. That seems to make sense. And accelerating to the left again. Now, well, we don't know the total now. I'm deliberating whether writing the formula is even going to help us. Let's try it at least. F net equals ma, so F1 plus F2 equals ma. Force number 1 is 25, but they haven't said in which direction, so I'll put plus or minus 25 and we'll decide which in a minute. F2 is 20 to the right, so it's definitely a plus 20, equals a mass that they never have told us. All they tell us about the acceleration is that it's negative, it's to the left, which means this total here has to be to the left, or it has to be negative. If both of these are pluses, we'd get plus 25 plus 20 would be plus 45, and that would be to the right, so that can't be it. It can't be the plus version. It must be the minus 25. Then we get minus 25 plus 20 is negative 5, and that means we're accelerating to the left. So this 25 would have to be oriented left. 25 newtons left and 20 to the right would leave you with 5 newtons left, and that would give us the acceleration we need. And it means our net force would be 5 to the left. And I forgot to fill in this one. It is 0 because constant velocity. Fair enough. So not all of these worked amazingly with the Newton's second law, but they did all work. You can always start with this, and then for net force you have to think how many forces are there that are adding up to this total. In this case there were always 2. Sometimes it's more, sometimes it's less, but this is almost always a good place to start. What else have they got here? Okay, assorted elevators. And we're supposed to do free body diagrams for them. You know what? I'm going to do something right off the bat because I think it'll make this easier. As long as we are on Earth, and every elevator I know about is on Earth, gravity is going to be pulling down. So we're always going to have an FG oriented downward. We can put that in right away. Gravity doesn't care how you're moving. It always pulls in the same direction equally hard. So that force is guaranteed. Now, if all these elevators have gravity pulling them down, why don't they crash to the floor? Because there's cables attached to them which hold them up. And if an elevator's sitting still, then we have cable tension, and also there are roller brakes and some other mechanisms I'm not super familiar with, but let's mainly go with cables. There'd be a gravitational force pulling down, and there would be a tension pulling up, and this elevator just hangs from its cables and doesn't move at all. Constant velocity, remember, is the same as stationary as far as the forces are concerned. If you're sitting still, if your speed is 0, 0, 0, or if your speed is like 6, 6, 6, either way, your acceleration is 0, and that means your net force is 0, and that means all your forces are canceling out. So both of these elevators are in what we call force equilibrium. The total force on them is 0, so they just cruise at whatever their current speed is. This one sits there at constant 0, this one sits there at constant plus 6 or whatever, and neither of them is accelerating. If an elevator is accelerating downward, what happens then is the cables go a little slack. So we get a smaller tension force. The motors that control the elevator are letting it fall a little bit. It's like when you let out a rope through your hands, and you're not just letting it drop because you get rope burn then, but if you let it out slowly, so it runs over your hands, the object is lowered at a controlled speed. So gravity pulls the same amount as always. Earth doesn't care what you're doing, it always pulls equally hard, but we're producing less tension, letting the elevator sink. And if you're accelerating upward, again, Earth pulls down the same amount as always, but if you want to lift something, you must pull harder. So the motor has to increase the tension on the cables, put in a little more work so that this force is greater than the elevator's weight. If you pull up harder than the elevator's weight, it will rise, and that's what's happening here. Fair enough?